then restarted it. And it was fine. Okay, thank you. So anyway, I was just asking everybody to write the electron configuration of bromine. Now I know that we've learned how to shorten electron configurations by using a noble gas core. Let's not, for this exercise though, I'd like to ask you to try to do the electron configuration from 1s. So go ahead and take a moment. You should have your periodic table out. What would be bromine's electron configuration? Yeah. Yeah. Not many. After this test, we're down to one last quiz. It's going to cover chapters 8 and then a little section out of 9 and 10. So I'll say that we only have one chapter. There are 3 chapters in the book that we're going to be hitting, but it's really not that much. There will be a test, yeah. Test is going to be around April 30th or so. We'll be taking the test that very last week before the AP exam. We're going to have some review quizzes too. Just studying back to some of the older chapters. And we're not doing a group quiz. No, sir.
Then we can put all of our minus together and we can get 100 on it.
So what? Maybe you won't learn anything that way.
Our S orbitals?
All right. Our what?
S orbitals are always maxed out too.
Yeah.
But like if there's 2 elements on that row that has
2 elements in that row.
like, so like beryllium, that'd be the second one. But then it wouldn't have 4 electrons.
All right, Jenna, I don't know what you're trying to say. Let's go through this one, and if you have any questions about it, let me know. Mina? Bracket. Yep. Square it up right now. Okay, so for bromine, starting at 1s, remember that the S region and the P region, S is on the left, P is on the right. Whatever row number an element is in, that's the energy level for the S's and the P's. The D's being in the middle there, they're 1 less than the row number, their energy level is. So it goes 1s2, 2s2, 2p6, that takes us through the second row. We're at neon right now, keep going. 3s2, 3p6, that's taking us now to argon. Keep going. 4s2, then after 4s2 is 3d10, and then 4p5. Get those? Okay, so that's the electron configuration. Jennifer, do you know what you were trying to ask me a minute ago?
It's all good.
Okay. I'm going to ask you to try a couple other electron configurations. We're not going to just keep doing the same thing. But what about if we have an ion? The sulfide ion, S with a -2. What would be the electron configuration of S with a -2? Yeah. Yeah, but I want everybody to write it out first. Yeah, so what does that -2 mean? It's got 2 added electrons, yeah. Don't take away 2, add 2.
Yeah.
Would sulfur's second ionization, or no, second electron affinity act similar to chlorine's first electron affinity?
We don't talk about multiple electron affinities. We do for ionization energy, but we don't say first, second, third electron affinity.
So what about like
It should be-
scandium second? Oh no,
it should be the same.
calcium second electron affinity. Would that be similar? To
Why are you asking? I just told you that we don't use multiple.
ionization energy?
Oh, okay.
My bad. Calcium second ionization energy comparing that to potassium first ionization energy. Would they be the same?
No, because calcium has a higher nuclear charge, so calcium second will be higher. It takes more energy to remove calcium second, even though they both have 18 electrons. Calcium's got more than that. Okay, so now we have sulfide. 1s2, 2s2, 2p6, 3s2, 3p. Now, when sulfur was neutral, it ended with 4 electrons and 3p. But since it's a -2, 2 electrons are added to it, and we would change that 4 to a 6. Yes?
So if it was like, if in neutral it was like 3p6, then would you have to add a new particle on?
Yeah,
What do you think
and
was-
don't count on that happening. I mean, once you have a noble gas arrangement, it'd be like argon becoming an ion by gaining 2 electrons. You'd say, well, it wouldn't do that. Well, you're right, it wouldn't do that. So that's what you're asking, though. Yes, you would have to start into the next energy somewhere. Yep.
So how do you know that that's not argon?
I guess, yes, it's possible. Yes?
So if it was like a plus sign, just take away stuff.
Yeah, you use
Right, that's the next one I'd like to try, is iron with a +2. We call this the ferrous iron. When a name of a metal ends with OUS, that means it's the lower oxidation state. Iron can be +2 or +3, so if it's +2, we call that ferrous. If it's empty +3, we call it ferric. Yes?
So for the sulfide ions, if you're given an electron configuration as what it is, how do you know it's not argon?
You would have to be told what -2 element is that or something like that. Otherwise, you just say, oh, that's argon. Yes, Johnny.
Get this?
Can you use one coefficient for 2 letters? Like for S and P,
4s1, 3.
be like 2S squared.
2s2p6.
But
We never do that.
Remember,
Oh,
it
no,
was
it's
an
on the-
action electron from the
Oh.
just to
Yeah,
satisfy.
okay.
They're just shortening it so they can fit it in that that
Yeah.
thing. I guess you could.
No, but
Then
it's
what they also did was for that to work, they switched the order.
Yeah, they just switch the order sometimes, especially when you're getting into the D's. They'll do like 3S, 3P, 3D, and then go on to the 4th.
Yeah.
Yeah, it's fine. It's fine. Whichever order you put them in, it's fine.
Also, 4s1.
Okay, now I was purposely withholding information on this one. This may not be what you expect. Iron when that's +2, we've got 1s2, 2s2, 2p6, that's the second row. 3s2, 3p6, that's the third row. 4s2, 3d6. This is neutral iron. Now we need to make it a +2, which in this case we have to remove 2 electrons. So you probably think, oh, you would just take that 6 down to a 4. It's not right. And Ruth, what do you do then?
You take an electron from the 4s orbital and bring it to the 3d.
Nope, we don't do that either. We have to get rid of 2 electrons.
It has to be an empty.
Oh, never mind.
These 2 electrons are the ones that we get rid of. Those 2 electrons. Even though the d electrons supposedly are highest in energy and they're the farthest away from the nucleus, when transition metals form ions, they always make positive ions, remove their s electrons first, even if it's not the last term in the configuration. I'm going to write that down and suggest that you write it down for yourself. Transition metal ions or transition metals form ions by losing their s electrons first. So, I'll get out of your way in a second. Writing the correct configuration, it would be, no, 3p6, 4d. I did it again. 3D, not 4D. There. What? No, don't put 4s0. Just get rid of the 4s term. I guess if you put 4s0, I'm not going to mark it wrong. Yes, Amber?
In the answer key, they just took one off, so it's 4s1 and then 3d5.
What? They did?
Yeah.
I've never seen that before.
Wait, 4s1,
Those crazy Zoom dolls.
Zoom dolls make yet another mistake.
Wait, what did they do?
Maybe I'm the one making the mistake.
Or maybe it's me. It's possibly
Did
me.
you say 4s1?
Yeah.
What do you think those are number wrong?
Look it up.
There are many kinds.
Many.
It's actually
Don't be silly.
So it would have an empty
Two is a
orbital
huge
and it would
number.
just jump up.
What's that?
It would have an empty orbital and it would just jump up.
Yeah, no. There are exceptional electron configurations. It is true that the D sublevels tend to be more stable if they can be completely full with a D10 term, or even half full is very stable. So that's what the Amber is claiming that the solution guide says. It says that they would keep one electron in 4s and only 5 in 3d because that would make the 3d half full. There are other cases where, for instance, one of them would be chromium. Chromium, if you look at the electron configuration of chromium, it would be 4s2, 3d4. Chromium's ground state, though, actually kicks one of its 4s electrons up to make 4s1 and then 3d5 to make that d half full. I'm not going to hold you responsible for that half fill rule. You may have learned it in Chem 1. I know I teach that in Chem 1, that the D is more stable when it's half full or completely full. The College Board vowed that they would not include that in the exam, and so I'm blindly going to trust them. It's dumb.
You can't trust them.
So,
We'll look at it.
Just be aware when you're doing the problems, there may be a problem or two that asks about copper, chromium, or whatever, and it's because they're exceptional electron configurations. I'm not going to have you responsible.
So, for example,
Yeah,
we put it as 4s2, 3d4.
Yeah, that would be fine. I'm not going to mark you down. I'm not grading the AP test, but on a Quizzer test, I'm not going to even bother putting those in. The truth.
What about something like this?
Yeah, no, I would expect you to know that the 4s electrons come out. Now, did you find that one, Amber?
Yeah, they had it.
So it's written as 4s1, 3d5.
Yeah.
Okay.
Is that because it's half?
Yeah, because they will. There's going to be a section in there where they'll talk about the electron configurations and the exceptions. That is an exception. We're not going to worry about it. Assume that all the s electrons come off the transition metals first. Yes.
Could we rate 4s1, 3d5 on that?
Knock yourself out.
So both forms.
So it's
Both forms are right.
Yes.
That was different.
I do expect you, though, to remember what I have written up here in red. Get rid of the s electrons first. That's the take home. Okay.
Yep.
All right. Anything else about electron configuration?
We did do that.
Let's continue. And I'm not going to have you do that one. I'd like to go through this pretty quickly. I don't want you to draw any graphs. I have almost every slide has a graph on it. The book has graphs in it. You don't need to copy the graphs down. I'm not even sure how much you need. If you understood what you were reading about ionization energy and atomic radius and all that yesterday, then I don't think you need to write a whole lot down. When we get to the weird things, then maybe we want to write stuff down. Ionization energy is the first property that we'll take on. Ionization energy is how much energy it requires to remove an electron. Normally, this is done by taking a vapor of matter, like oxygen gas or nitrogen gas or carbon vapor or even the metals, transition metals, sulfur gas, phosphorus gas, silicon gas. You normally will hit that with specific energies of X radiation, and that will cause the electron to go flying off, go into something else. So it can be measured.